Okay, students, so let's get started with past papers for light and lenses. These are theory past papers and are applicable for both O levels and IGCSE physics. So let's start with the first question. Figure 5.1 shows part of the ray diagram of a lens being used as a magnifying glass. Three rays are shown coming from the top of an object O. Okay. The point labeled F are one focal length from the lens. Okay, this is one focal length F and F. Okay. State the name of the type of lens shown in figure 5.1. This is a converging lens. This is a converging lens. Okay. Describe what happens to the ray of light R as it enters the lens. Okay. So initially your light is in air. As you enter the lens, probably you are entering glass or plastic. So you are going from a less dense material to more dense material. As you go from a less dense material to more dense material, what happens? Light bends towards the normal. Simple as that. Okay. What will happen as it leaves the lens? It becomes parallel to the principal axis. Parallel to the principal axis. Simple. Using all three rays from O, complete figure 5.1 to show the image formed. Okay, we have to. So using all three rays from point O, complete figure 5.1 to show the image form. Very easy. You already have one ray extended. You can then take this ray and extend it backwards like this. 1 second. Somewhat along these lines. Let me align first of all this ray. Yeah. And what you can do is you can erase this thing. You can erase this thing. And this is where your image is formed. This is your image I. How did I located this image I? Very easy. First of all, I extended the optical ray, the ray that was passing through the optical center, this one, extended it backwards. It was already done for me in the examination. Then I took this ray passing through the focal point, extended it backwards. The intersection of the two rays give me the image point. Okay. Underline all the words in the list that describe the image formed in C. What words describe this image formed in C? This is virtual and this is upright. Simple. Let's further move ahead. Figure 3.1 shows a light entering a transparent block. Okay. Light enters the block at an angle of theta to the normal and travels through the block until it reaches the bottom surface. The angle between the ray in the block and the vertical side of the block is phi. Okay, this angle is phi. Okay. Light travels more slowly in the block than in the air. Explain how figure 3.1 shows that. We have to show that light travels more slowly in the glass block than in air. How does figure 3.1 show that? Very, very easy. You can see light bending towards the normal. This indicates that light is going from a less dense material to more dense material. Hence, light is traveling slowly. You can write here. Light light bends towards the normal, towards the normal, indicating that light is traveling, light is traveling from a less dense material, from a less dense material to a more dense material, to a more dense material. This shows a decrease in speed, a decrease in speed. Simple. State what happens to the wavelength of light and what happens to the frequency of light as it enters the block. Obviously, if speed decreases, wavelength will also decrease and frequency remains same. Let's further move ahead. The refractive index of the transparent material is 1.6. Angle theta is 45. You have to calculate angle phi. Okay, so angle theta is 45. We know that the refractive index is 1.6. The n here is 1.6. We have to calculate this angle r. First of all, can we do that? Yes. This transparent block is the second medium, you can say. What was the refractive index formula for the second medium? Refractive index for the second medium is equals to what? Sine I over sine R. What is the refractive index? 1.6. Do you know sine R? No. Do you know sine I? Yes. Sine 45 divided by sine R. Can you calculate the angle of refraction? Yes. Pretty easy. Sine R is equals to sine 45 divided by 1.6. So sine 45 divided by 1.6 and sine inverse, your R comes out to be 26.2 degrees. But if you notice, you didn't need R, you need the angle phi. What will be the angle phi? 90 minus R. So 90 minus the angle, your phi comes out to be, phi is equals to 63.7 degrees. You can write it here, phi comes out to be 63.7 degrees. Now let's move on to the next part of this question. The angle of incidence I at the bottom surface is equals to phi. What was phi coming out to be? 63.7 degrees. And the critical angle for the material of the block in air is 39 degrees. You have the critical angle as well. Explain what happened to the light after it meets the bottom surface. Okay. So this phi is 63.7 degree and this angle of incidence is also 63.7 degree. This is greater than the critical angle. What will happen? Total internal reflection. Total internal reflection. So you can say since angle of angle of incidence is greater than the critical angle is greater than the critical angle, what happens? Total internal reflection occurs. Simple as that. Let's further move ahead. Figure 5.1, okay, shows light in air incident on the side of a rectangular glass block at an angle of 60 degree. This is your angle of incidence. The refractive index of glass is 1.6. Looks like a pretty similar question to the previous one. Okay. The light travels in the glass and is incident on side XY. Okay. Underline all the terms that describe a wave of light: electromagnetic, not longitudinal, not radioactive, transfers. Yes. At the point where the light enters the glass, at this point, calculate the angle R. We have to calculate the angle R. We know n is equals to what? Sine I over sine R. What is n? 1.6. What is sine I? Sine of 60 divided by sine of R. R comes out to be what? Sine inverse of sine 60 over 1.6. So sine 60 divided by 1.6, sine inverse, your answer, this comes out to be what? 32.7 degrees is your answer for angle of refraction. Let's see this. Calculate the critical angle for light traveling in the block. We have to calculate the critical angle. What have we studied? Critical angle, sine of critical angle is equals to 1 over n. Or at least we have studied this formula. Refractive index is 1 over sine of critical angle. We can apply any one of these formulas. They are one and the same thing. Do you know the refractive index? Yes, 1 upon 6. So sine of critical angle is equals to 1 over 1.6. Critical angle is what? Sine inverse 1 over 1.6. Can we calculate this? Sine inverse 1 divided by 1.6. This gives you a value of 38.7 degrees. Critical angle is 38.7 degrees. At P, the angle Q between the ray and the normal is 90 minus R. Okay. This angle is 90 minus R. What was your R coming out to be? 32.7. So 90 minus 32.7. This gives you a value of what? 90 minus 32.7. This gives you a value of 57.3 degrees. Okay. So your angle theta is 57.3 degrees. You can write it here 57.3 degrees. As you can see, this angle theta is coming out to be greater than the critical angle. What will happen? Total internal reflection. Exact same answer to what we have done in the previous part. Since angle of incidence is greater than the critical angle, total internal reflection happens. You can write critical angle here. This exact same answer will be copied here. No changes. Let's move on to the next question. Okay, let's see this. Two mirrors A and B are inclined at an angle of 60 degree to each other. Light strikes mirror A at an angle of 30 degree as shown in figure 4.1. Okay. Determine the angle of incident at mirror A. So angle of incidence is the angle between the normal and the incidence ray. This comes out to be 60 degree. Okay. Determine the angle of incidence at mirror B. Angle of incidence again is the angle between the normal and the incident ray. Here both of them are aligning or overlapping each other. So angle of incidence becomes 0 degree. Describe the path of the reflected ray after it leaves mirror B. Okay, after it leaves mirror B, what will happen? It will reflect back along the same path. Along the same path. Simple. Let's further move ahead. A mirror hanging on a wall is used to form an image of an object. State three characteristics of the image formed: virtual, upright, and image is of the same size. Is of the same size as the object. As the object. Simple as that. Let's move on to the next question. A dentist uses a plane mirror to see the back of a tooth. Okay. A plane mirror produces an image of an object. Describe the position of this image. The perpendicular distance, perpendicular distance of the image from the mirror, from the mirror is equal to what? Perpendicular distance, perpendicular distance of the object from the mirror, of the object from the mirror. Okay. And can we add any other thing here? We can say that the image will be behind the mirror, will be behind the mirror. Let's further move ahead. Okay, so let's look at part B. Figure 6.1 shows the plane mirror used by the dentist to see the point X on the tooth. On figure 6.1, mark the position of the image X formed by the mirror. Okay, so we remember one thing, that the perpendicular distance of the object from the mirror, that is, let's say this distance, will be same as the perpendicular distance of the image from the object. I'm just eyeballing it. Let's say this is your, you can say this is your image X. No, X is the object, right? So let's label this as image I. And then we can erase these lines if you want to. Okay, now what's next? Draw a ray of light from X to show how the dentist can see the tooth. Very, very easy. What will you do? You will create a ray of light from this image into the eye, like this. And you will make sure to do one thing. You will make the backward part dotted because it is an imaginary light ray. And if you are smart enough, you will also draw a light from here till the mirror, somewhat like this. Yeah. And further, if you are literally an A star student, you will draw a normal like this. You can show angle of incidence, angle of reflection like this. Simple. State one characteristics of the image formed by the plane mirror other than its position, it is upright. Let's move on to the next question. Figure 3.1 shows three rays of light traveling in water from a light source. Okay. One ray of light is totally internally reflected at the boundary between water and air. Okay. On figure 3.1, mark the critical angle and label it C. Okay. Where is the critical angle? This. Critical angle is the angle of incidence at which the angle of refraction becomes 90 degree. This is the only case. State why only one of these rays is totally internally reflected, because only one ray has an angle of incidence greater than the critical angle, greater than the critical angle, than the critical angle. Simple. Let's move ahead. Calculate the refractive index for water. We have to calculate the refractive index for water. How will we do that? We know, do we know the critical angle? No. But we know the angle of incidence I here, we know the angle of refraction 34 here. So we will say n is equals to sine r over sine I. Why sine r over sine I? Because water is my first medium. If you have to calculate the refractive index of the first mediums are those mediums from which the ray starts. You can refer to the recorded lecture as well, or the lecture posted on YouTube as well, for further understanding. Water is the first medium, so we will use this formula. Sine of 34 divided by sine of 25. What will your answer for refractive index come out to be? 34 divided by sine of 25. This gives you a value of 1.3. Your refractive index is 1.3. Please remember this formula for first medium. Refractive index is 1.3. Calculate the critical angle. Very easy. Critical angle is what? N is equals to 1 over sine C. You have your n. What will you do? 1 divided by 1.3, take a sine inverse of this, you will get your critical angle. 1 divided by answer sine inverse. This gives your critical angle of 49 degrees. Simple. Ultraviolet radiation is one component of the electromagnetic spectrum. Okay. State the name of two components of the electromagnetic spectrum that have a smaller wavelength than ultraviolet radiations. Which components have a smaller wavelength than ultraviolet radiations? X-rays and gamma rays. This was just a thing that you can only do by memorizing stuff. Gamma rays. Let's do that. Gamma rays. State one useful application of ultraviolet radiation. Security alarm systems. Security alarm systems. Okay. Exposure to ultraviolet radiation from the sun damages the eye. State one type of damage to the eye caused by ultraviolet rays. Damage to the retina. Damage to the retina. Okay. Let's further move ahead. Figure 7.1 shows a ray of light. The ray passes into a semicircular block of glass at A and leaves the glass at B. Okay. Traveling along the surface to C. Okay. State the name given to the angle of incidence marks as 40-degree critical angle. Critical angle. Calculate the refractive index of glass. We have to calculate the refractive index of glass. Again, n is equals to 1 over sine C. 1 divided by sine of 40. This gives you a refractive index of what? 1.5. 1 divided by sine 40 is equals to 1.5. 1.5 is your answer for refractive index of glass. Let's further move ahead. Let's see this. Figure 4.1 shows a ray of white light incident on a glass prism. Okay. Refraction causes the white light to separate into different colors. Define the term angle of refraction. Between angle between the normal and the refracted ray. Angle between the normal and the refracted ray. Simple. Let's move on to part B. The angle of incidence of white light as it enters the prism is 40 degree and the angle of refraction is 25 degree. Calculate the refractive index of the glass for red light. Show your working. We have to calculate the refractive index for glass. For red light, what will we do? N is equals to sine I over sine R. What is your angle of incidence? 40 degrees. What is your angle of refraction? Sine 25. This comes out to be what? Yeah, we have taken the correct angles. Sine 40 divided by sine 25. One second. Why are we getting. Oh, yeah. So sine 40 divided by sine 25. This comes out to be 1.52. This is your refractive index of the glass for red light. Okay. Use figure 4.1. State and explain how the refractive index for red light differs from the refractive index of violet light. So, violet light bends more. So, the refractive index of violet light will be what? More. So, you can say violet light bends more, having a lesser angle of refraction. Angle of refraction. Hence, violet has a greater refractive index. Greater re refractive. Oh, greater refractive index. Simple, nothing complicated. I hope you guys are getting things. The source of white light placed in figure 4.1 produces other types of electromagnetic radiations as well as visible lights. State the name of the invisible radiations found at P and the invisible radiation found at Q. Okay. So the radiation found at P must have a wavelength greater than red light, infrared radiation, and uh, the element found at Q or the radiation found at Q must have a wavelength less than violet. So ultraviolet rays, ultraviolet radiations. Simple. You can copy this down in the spaces below. Let's move ahead. Two parallel rays of light, one red and one blue, enter a glass prism. Okay. Figure 4.1 shows both rays of light before they enter the prism. Okay. The blue ray is also shown incident on a different side of the prism after passing through the prism. Okay. The ray of blue light strikes the left side of the surface at a critical angle. Okay. On figure 4.1, mark and label the angle of incidence and the angle of refraction for the blue light as it enters the prism. So, angle of incidence is the angle between the incident ray and the normal, and angle of refraction is the angle between the normal and the refracted ray. On figure 4.1, continue the path of the blue light after it strikes the left side of the prism. So, if this is critical angle, the light will start to travel along the surface like this. The light will start to travel along the surface like this. Oh, actually, one thing that you shouldn't learn from me is drawing. Literally, even the simplest of drawing tease me. So, this is your path. The refractive index of glass for red light is smaller than the refractive index of blue light. This is what we have discussed in the previous question as well. On figure 4.1, draw the path of red light as it travels in the prism and after it strikes the left side of the prism. Okay. So we have to take care of one thing. What is that thing? We have to make sure that red refracts less. So somewhat like this, maybe. And this is your angle of refraction. This is your angle of incidence. And as you move through the prism. So let's draw a normal here as well. Let's say this is your normal. One second. let's draw the normal with a black color so that it differentiates. So yes, here you can see I have drawn a normal with a black dotted line, and red light refracts less or bends less than blue light, and as it goes outside the prism, what happens? It bends away from the normal. So yeah, this is what you had to draw here. State what is meant by critical angle. Critical angle is the angle of incidence when angle of refraction becomes 90 degree. When angle of refraction becomes 90. The angle of incidence when angle of refraction becomes 90 degree is known as critical angle. The refractive index for the refractive index of glass for blue light is this. You have to calculate the critical angle. Very easy. N is equals to 1 upon sine C. Sine C is equals to 1 over 1.5. C is equals to what? Sine inverse 1 over 1.5. What does this equals to? 1 over 1.5. This comes out to be what? 41.8 degrees is your critical angle. Let's further move ahead. A thin converging lens is made of transparent material of refractive index 1.5. This is your refractive index. Okay. A ray of light traveling in air strikes the surface of the lens at an angle of incidence 55 degree. This is your angle of incidence. Calculate the angle of refraction. What have we studied? N is equals to sine I over sine R. You have sine I, you have N. 1.4 is equals to sine of 55 divided by sine of R. Can you calculate R? Yes. Sine inverse sine 55 divided by 1.4. What does this equal to? Sine 55 divided by 1.4. Sine inverse, your answer. This comes out to be 35.8 degrees. Simple. Place a tick in one of the boxes in the third column of table 8.1 to indicate how the light ray deviates and what happens to the speed of light in the ray as it enters the lens. Okay. So basically, as light is entering the lens, what is happening? You are going from air to glass. Okay. And you are going from less dense to more dense. Okay, whenever you go from a less dense material to more dense material, first of all, your speed decreases. So all these options get cancelled out. And as you go from less dense to more dense, what happens? Your light bend towards the normal. This fourth box is your correct answer. State what happens to the frequency of light. It remains same or unchanged. It remains same or unchanged. Okay. The focal length of the lens is 2.5 centimeter. What is meant by focal length? The distance between the optical center between the optical center and the principal focus and the principal focus. The distance between the optical center and the principal focus is known as your focal length. Let's further move ahead. The focal length is 2.5. Okay. Let's write it here just in case we might need it in this diagram, I guess. Figure 8.1 is a full scale diagram that shows an object O of height 3 centimeter and the lens. Okay. By drawing on figure 8.1, locate and mark the image I of object O. Okay. So we have to mark the image. This is our object. Let's first of all do one thing. Let's first of all mark the focal length. So this is 1, this is 2, and 2.5 will be, yeah, somewhere here. This is your focal length. 1, 2, negative. This is also focal length. Okay, perfect. This is also focal length. This is also focal length. Now let's locate the image. Okay, to locate the image, do you remember we used to have two lines? Okay, let's take a thin ray so that we make no errors here. This is the line passing through the optical center like this, and let's arrange it correctly from the top of the arrow. And yeah, I guess this is enough. isn't it? Yeah, this is enough. What will be your second ray? Your second ray will be parallel to the principal axis. Your second ray will be parallel to the principal axis. Now, let me tell you one thing. Why will this never align here? Oh, why will this never align here? Let me tell you. Because these are scanned documents, and when I scan them, maybe the alignment has somewhat. Okay, let's do one thing. If this is curving here, yeah, this is a quick fix. Okay. So this is a ray parallel to the principal axis, and this will pass through where? This will pass through the focal point here, somewhere. Let's mark this as well. Yeah. No, we should also close this further. Somewhere here, and if it passes through the focal point, yeah. Perfect. Here. Okay. Where is the image forming? Image is forming somewhere here. That I think is 3.1 centimeter away from the lens. Yeah, 3.1 centimeter. Okay. Not 3.1. Let me see. Let's zoom in. So this entire distance is 3.2 centimeter. I don't know whether we need it in the question or not, but we will see. Just doing it for the sake of it. Let's see. Determine the distance. Very good. See, this is what happens when you have done enough past papers. Determine the distance of the image from the lens, that is 3.2. We have already calculated. And then what you have to do? Then you have to determine the magnification produced. How can we determine the magnification produced? Very easy. Distance, magnification has a very simple formula. Distance of image from lens divided by distance of object from lens. So let's see the distance of object from lens as well. This is 1 centimeter, 2 centimeter. Okay, let's do this in a different highlighter color. This is 1 centimeter, 2 centimeter, 3, 4, 5, 6, 7, 8, 9. Okay. So this distance is 9 centimeter. This is 3.2 centimeter. Can you calculate the linear magnification? Yes, 3.2 divided by 9. Let's do that. 3.2 divided by 9. Your answer comes out to be 0.35 is your linear magnification. Describe how a converging lens is used in a camera. Okay, how is a converging lens used in a camera? How will you answer this? First of all, you will say light from the object gets refracted by the lens by the lens by the lens. The lens is adjusted by moving forward and backwards, by moving forward and backwards. Third point, adjust or place or fix the lens at a point where you find a real image. Simple. Let's move on to the next question. Light travels along optical fibers by total internal reflection. State two differences between total internal reflection and reflection in a mirror. For total internal reflection, what should be the case? Angle of incidence should be greater than the critical angle. Angle of incidence should be greater than critical angle for total internal reflection, and reflection can happen at any angle. Let me write it. I hope you can write these differences. These are also given in the notes. Total internal reflection has this, and reflection happens at any angle. Happens at any angle. The second difference, for total internal reflection to occur, you must go from a more dense material to a less dense material. For total internal reflection to occur, you must go from a more dense material to a less dense material. Okay. And there are no such restrictions for reflection. The critical angle for light traveling from the material of the fiber to air is this. This is your critical angle. Calculate the refractive index of the material. N is equals to 1 over sine 44. 1 divided by sine 44. This comes out to be what? 1.44 is your refractive index. Light enters the optical fiber from the air at an angle of incidence. This calculate the angle of refraction. Very easy. We already know the refractive index. 1.44 is equals to sine I over sine R. 1 second. Sine I over sine R. What is your sine I? Sine 50. Sine R is equals to sine 50 over 1.44. R is equals to what? Sine inverse sine 50 over 1.44. So sine of 50 divided by 1.44. Take a sine inverse. Your angle of refraction comes out to be 32.1 degrees. Simple. Optical fibers are used in telecommunications to send large amounts of data. State two advantages of using optical fibers rather than wires for transmitting data. More secure, more privacy, or more security, you can say. And secondly, optical fiber cables are much lighter compared to other types of cables. Let's move on to the next question. Let's see this question. The virtual reality headset in figure 6.1 shows contains a display and a lens as shown in figure 6.2. Okay. This is the virtual reality headset. This is the display. Okay, let's further move ahead. The display is the object for the lens. Okay, so this is the object for the lens. The lens acts as a magnifying glass and forms a virtual image of the display. Okay. Describe where the display must be positioned relative to the focal length of the lens for the lens to act as a magnifying glass for the image on the display. For a lens to act as a magnifying glass, what should happen? For a lens to act as a magnifying glass, the object or the display should be placed where? The object or the display should be placed between the optical center and the focal point, should be placed between optical center and the focal point, between optical center and focal point. Simple as that, nothing complicated here. Let's move on to part 2. Explain how a virtual image is formed extending by extending the diverging rays, by extending the diverging rays backwards. If you extend the diverging rays backwards, this will form a virtual image. This was our case number 5 in converging lens lectures. Okay, let's see part B. An arrow on the display is 3.4 centimeters from the lens. Okay. The virtual image, of the arrow is 22 centimeters from the lens. Okay, these both things are given. Figure 6.3 shows the arrow O and the lens L and the virtual image of the arrow I, okay, drawn on a grid with a scale of 1:2. Okay. On figure 6.3, draw a ray diagram to show the formation of the virtual image. Very easy. Okay, how will you draw the ray diagram? First and foremost, take a thin pencil and draw Oh, this is not thin. This will create errors. Do we have a thin area? This will do the job. First of all, create a ray that passes from the top of both the arrows and then through the optical center like this. This should be your first ray. Although this is not passing through the optical center, let's slightly adjust this. Yeah, somewhat like this. I think we will need to adjust it from the top as well. Yes. This looks fine. Yeah, that's fine. So this is your first ray passing from the top of both the arrows and then passing through the optical center. How will your second ray look like? Now this is a very good question. Whenever we are drawing ray diagrams, our second ray is parallel to the principal axis, something like this, something along these lines, and it passes through the focal point. But here we don't have the focal point. But here we don't have the focal point. What will we do? We will say that if we extend this ray backwards, this will be the first point, this will be the second point. We connect both these points to get a second ray, somewhat like this. See, what have I done here? Let me tell you. I know that the image will be a virtual image because it is formed from a magnifying glass. Okay. If my image is a virtual image, that means my rays must be extended backwards. If I want to extend the red ray backward, I first of all need to pass it somewhere through the focal point. But I don't have the focal point currently. But I know one thing. That this ray, red ray, will have this as its point and this as its point. Because this is the image formation basics. Now, this is how your virtual image gets formed. Determine the focal length. You have to determine the focal length. So, what will you do? You will extend this line with the same slope. You will extend this line with the same slope. Let me utilize this line with the same slope. Yeah. And let's see what the answer for focal length comes out to be. Let's zoom in a bit. The answer for focal length. This is 1, 2, 3, 4, 5. Every 5 boxes, can you see here? One second. Every 5 boxes on the x axis represent 2 centimeters. So if you can see here, 1, 2, 3, 4, 5, 2 centimeter, 1, 2, 3, 4, 5, 2 centimeters. So we have roughly here that is 3.9 centimeter is your focal length. 3.9 centimeter is your focal length. This is your answer. So let me give you a recap for this. What have I done here? First and foremost, I know that this will be a virtual image, especially from the diagram as well. It is evident. And first of all, I know that it is a magnifying glass. Magnifying glasses form virtual images. Once I know that, I have been given the position of the image and position of the object. I made a ray, that is this blue ray, passing through the image and the object and then through the optical center. Then I made a ray that is passing from the image and is connecting with this red ray that is parallel to the principal axis. Simple. And then you extended this green ray to calculate the focal length. Simple as that. If you need further explanation of this question, you can ask in the chat below. Okay, let's see this question. A parallel beam of light traveling in air is incident on a glass lens. The beam is perpendicular to the glass lens as shown in figure 8.1. The dash line indicates the position of the lens P. Okay. The center of the lens is dot C. Okay. The lens is diverging lens. On figure 8.1, indicate the shape of the lens by drawing the outline of the lens around the dash line P. So basically, the lens will look something like this. A biconcave lens. somewhat like this. Not, we have curved it a bit too much. Somewhat like this, and somewhat like this. Oh, these drawings are pretty difficult. Yeah, your converging lens looks something like this. Okay. Let's move on to the next one. Draw the part taken by each ray of light after it passes through the lens. Okay. What will happen as each ray passes through the lens? The ray passing through the center will remain like this. These extreme rays will diverge like this. Okay. Let's move on to the next part. Diverging lenses are used to correct short sight. Figure 8.2 is the simplified diagram of a short sighted eye. Okay. Light from a distant object strikes the eye lens and enters the eye. On figure 8.2, continue the three rays in the eye until they reach the back of the eye. Okay, so if this is a short sighted eye, what will happen? The images will form before retina, somewhat like this. Let me extend this, and let's extend this middle line as well. Hmm. Let's extend this here, and let's extend the last line as well, somewhat like this. Yeah, the image forms before the retina if this is a short sighted person. This is your image eye. Okay. Let's further see. State how the image of a distance object detected by a normal eye differs from the image detected by a short sighted eye. A normal eye, a normal eye detects a sharp focused image. Detects a sharp focused image. Simple. Let's move on to part 3. Explain how a diverging lens corrects the sight of a short sighted eye viewing a distance object. It diverges, it diverges the rays further. Simple. Let's move on to the next one. The focal length of the diverging lens is 4 centimeter. Okay. An object of height 3.5 centimeter is placed 6 centimeter from the center of the lens. Figure 8.3 is a full scale diagram drawn on a grid on which the dashed line L represents the length and the arrow O represents the object. Okay. So our focal length is 4 centimeters. So let's first of all mark the focal length. This is your focal length. Oh, this is your focal length F. This is your focal length F, and this is also your focal length F. Okay. Uh, what do we have to do? By drawing on figure 8.3, find the position of the image, draw the image I and label it as I. Okay. So as we have done it in every ray diagram, what will we do? First ray passes through the optical center like this. Second ray is parallel to the principal axis. One second. What can we do here? Can we do? Yeah, we can zoom in here and we can align it perfectly. Oh, one second. Yeah, let's align it perfectly. So, somewhat like this. Because the height of the object is 3.5 centimeter. So, I am doing according to that. Okay, your parallel to the principal axis ray has also been drawn here. Now, which type of a lens is this? This is a diverging lens. So, do you remember in a diverging lens, if you extend this ray backward, it will pass through the focal point. In a diverging lens, if you extend this ray backward, it will pass through the focal point like this. Okay, like this. And what do we usually do? We make this ray dotted. We make this ray dotted like this. Like this. And once we have made this ray dotted, the intersection of these two rays gives you the position of the image I. This is your image I. Simple. Let's draw an arrow here as well. This is your image I. Simple as that, nothing complicated. Let's move on to the next part. Explain whether the image produced is virtual or real. Virtual. Simple. On the grid in figure 8.3, write an E in a position from which an eye can observe. You can see this image. Okay, where can an eye see this image? An eye can see this image from here. Determine the linear magnification produced. Very easy. Determine the linear magnification. What will we do? Linear magnification is equals to what? Linear magnification. Okay, linear magnification is equals to what? Height of the object, height of image divided by the height of object. We already have the height of the object. That was 3.5 centimeter. It was given in the question here. Can we calculate the height of the image? Yes, we can do that as well. Let's zoom in a bit here. And if you notice, the image is at, these are five boxes equal to 1 centimeter, and then we have two boxes further. So the height of the image is here, that is 1.4 centimeter. Okay. So the height of image is 1.4 centimeter. The height of object is 3.5. Divide both of them. You will get your linear magnification. That comes out to be 1.4 divided by 3.5. This equals to 0.4 is your linear magnification. Simple as that. Nothing complicated. Let's move on to the next question. Yeah, let's see this. A converging lens has a focal length of 3 centimeters. Okay. So we have a focal length of 3 centimeters. An object is at a height of 2 centimeter is placed 5 centimeters from the center of the lens. Okay. Figure 6.1 shows the arrangement of the object and the lens. Okay. On figure 6.1, draw rays from the top of the object to show how the lens forms an image of the object. Mark the image clearly. Okay. First of all, what is our first step? Let's mark the focal length. 1, 2, 3. This is your focal length F, and 1, 2, 3. This is your focal length F. Okay. Now let's start making the rays. First ray passes through the optical center like this. Okay. From the top of the object and into the optical center. Simple. Okay. I guess, yeah, we need to tilt it slightly downwards. Yeah, passing through the optical center. The second ray is parallel to the principal axis. Second ray is parallel to the principal axis. 1 second. And it passes through where? It passes through the focal point. Somewhere here. So you will have your image like this. Maybe somewhat like this. And you have to zoom in and make sure that this starts from here. Okay, let's extend this as well. Okay, perfect. Let's tilt this so that it passes through the focal point. Yeah, let's extend this red line as well, making sure that we don't disturb its direction. Yeah, this comes out to be your image. Perfect, perfectly aligned. This is your image point. Okay, I. And we can also mark an arrow here, somewhat like, oh, let's do it with an arrow tool. The arrow is somewhat like this. Oh, this is your image. This is your image. Let's align the arrow as well. Yeah, somewhat like this is your image. Okay. The image is magnified. State one other feature of the image. Yeah, the image looks magnified to me as well. State one other feature of the image. The image is inverted. Okay, inverted. Calculate the linear magnification. Very easy. How will you calculate the linear magnification? Height of image divided by the height of object. If you notice, you are already given the height of the object. The examiner has been very kind to you. The height of the object is already given to you, that is 2 centimeter. Can you calculate the height of the image? Yes, the height of the image is 1 centimeter. 1 second. 5 boxes, 1 centimeter. 1, 2, 3, 4, 5. One more centimeter, and this is 2.4. Yeah, so this will be 2.8 centimeters. Okay, so 2.8 divided by 2 is your linear magnification. This comes out to be 1.4, I guess. Let me do it in the calculator as well because I'm not sure about it. 1.4 is your answer. Yeah. State the name of one optical device that produces a magnified image as shown in figure 6.1. Projector. Simple. Projector enlarges your images. So that's it for today's lecture. That's it for the light and lenses past papers. If you have any questions, you can ask in the chat.